If a bank or hospital wants to use blockchain technology today, they immediately run into a wall. Transparent networks like Ethereum or Solana are entirely public, meaning a company using them broadcasts every drop of its sensitive business intelligence to the world. But the alternative, total anonymity networks like Monero, operate in the dark, making it mathematically impossible to prove compliance to global regulators. We can see exactly where this vulnerability peaks in cross-chain bridges. This diagram shows a standard bridge transfer. The moment liquidity moves from one chain to another, the specific details, who is sending, who is receiving, and the exact amount, are permanently etched onto a public ledger for any competitor to analyze. Now, if we try to solve that by completely hiding the data, we hit the opposite extreme. When the transaction parameters are entirely masked, compliance alarms trigger. Without a way to verify that a transfer isn't tied to sanctioned entities or illegal activities, the exit path is blocked by regulatory firewalls. This is where the Midnight network comes in. Built as a partner chain to Cardano, Midnight introduces a concept called rational privacy. It allows us to build the ZK-Audit-Bridge, cross-chain infrastructure using zero-knowledge proofs, letting users selectively disclose specific pieces of data to specific people. Enterprise liquidity requires a system that is private by default to protect trade secrets, but compliant by choice to satisfy legal obligations. To understand how rational privacy works, we have to look at Midnight's architecture. This diagram shows its two intersecting ledgers. On the left, we have a public UTXO chain that handles network consensus and security. On the right, a private, account-based execution environment. Sensitive data stays on the user's local machine and never actually touches the public ledger. The tool that bridges these two environments is Compact, Midnight's domain-specific smart contract language. Compact allows developers to write the rules of a transaction and then generate a zero-knowledge proof that those rules were followed, all locally. Here is a look at a Compact smart contract for our bridge. Notice the opaque type applied to the transaction variables. This explicitly tells the network that the underlying metadata, like the sender's address or the transaction amount, must remain shielded from the public. But data cannot remain locked away forever if you are facing an audit. Compact includes a disclose function. This acts as a highly specific, programmable switch. It allows a user to reveal a targeted piece of shielded data only to an authorized party, like a tax authority, without unlocking the rest of the transaction. By moving the heavy lifting off-chain and only verifying zero-knowledge proofs on-chain, the system requires us to trust mathematical certainty rather than raw, exposed data. Let's see this in practice through our live application. In Phase 1, a user connects to our front-end interface and initiates a shielded cross-chain transfer. They input their deposit amount and destination address. Behind the scenes, the application does not broadcast those inputs to the web. Instead, a local proof server running on the user's machine calculates a ZK-SNARK proof. It verifies the math locally, creating a cryptographic receipt. This image displays the Midnight Explorer, showing exactly what arrives on the public network. You see a verified transaction hash indicating an action occurred and the math is correct, but all underlying values, the amount, the sender, and the destination, are completely hidden. To an external observer or a rival business tracking wallets, there is no usable business intelligence. There is only a cryptographic commitment. But businesses must operate in highly regulated environments. If an auditor needs to verify that this exact transaction did not interact with a sanctioned entity, the user grants them a specific viewing key. Looking at this split-screen interface, you can see the selective disclosure at work. On the left, the public still sees an opaque hash. On the right, inside the auditor UI, the viewing key successfully unshields a specific KYC-cleared risk flag for this exact transaction. One transaction viewed from 3 different perspectives. The bridge successfully proves regulatory compliance to the auditor without leaking a single byte of competitive data to the public network. Because the ZK-Audit-Bridge processes sensitive information entirely on the user's local machine, it natively enforces GDPR data minimization rules. The public ledger never holds the personal data in the first place, eliminating the risk of a centralized chain leak. To make this system viable for high-volume users, we utilize Midnight's dual-token economic model. This diagram illustrates how the core governance asset, the Knight token, automatically generates a secondary operational resource called dust. The bridge consumes that dust to process private smart contracts. This structure solves a major operational hurdle. By holding a fixed amount of Knight tokens, an enterprise bridge operator generates enough dust to cover their transaction fees over time, shielding them from the unpredictable volatility of gas fee markets. For institutions to deploy capital at scale, knowing exactly what their operational overhead will be is just as critical as ensuring their data remains private. Looking ahead, the protocol's interoperability roadmap expands this capability. Through an upcoming feature called Babel Station, external users will be able to trigger midnight transactions using foreign assets. A user on Ethereum could pay for a ZK-Audit-Bridge transaction using ETH, while the underlying zero-knowledge proof layer remains entirely abstracted. Our ultimate technical milestone is evolving our infrastructure. As this diagram details, we plan to transition from a federated bridge, which still requires trusting a specific group of relay nodes, to a fully ZK trustless bridge. In that setup, the bridge relies solely on a mathematical proof to connect state between two chains, removing the human element entirely. We invite the hackathon judges to explore this architecture themselves. You can test the selective disclosure features via the Versal link provided, and review our compact smart contracts directly in our open-source GitHub repository. The ZK-Audit-Bridge proves that privacy and auditability can coexist. It delivers the foundational infrastructure necessary for a compliant, privacy-first digital economy.